No, no. Co-host അല്ലേ ഇത്?
Hi, Mahesh. Hello, can you hear me?
Yes, I can hear you.
Ah, okay. Good. Do you want to share your slides? There is some camera problem this time.
You have a camera problem.
Now some camera, they are asking me to download something. I did. Okay, my camera is, if it is not working, still fine. I think you can review it. Yeah, I have a talk to give, but yeah, start.
You grant some access.
It should work now.
I'll have to, sorry, I'll have to
Yeah.
re-log in. So I'll
Okay,
be.
okay, do that. I will fix my camera by then.
Can you see my screen now?
Yeah, I can see your screen, but my camera is not fixed anyway. It's without that also too.
Do you see both, I mean, my screen and me?
Yes, I see both of you. Maybe I have to log out and log back in. I'm only worried if I log out, someone has to allow me to come back.
Yeah, so
maybe I can make you a co-host or something.
Now, so maybe I am a co-host now, so maybe I'll be able to.
Can allow me. Okay, let me now. Okay, it works. Okay.
Oh yeah. Hello.
Hi,
How are you?
I'm fine. So how are things? Are you in Bangalore? No?
Yes, I'm in Bangalore. I'm in my office.
You are not going to UK to get the shot?
No, I mean, probably prioritized older people and more vulnerable people anyway, but it's not a bad idea to continue this life for a few more months and see what the effects are of the
I
vaccine.
think that's everybody is thinking. Yeah. So how is the weather there? Is it chilly or?
It was a little bit chilly this morning. Um, 16. Ramurthy was complaining about being too warm at 5, and now I'm complaining about too cold at 16. So.
Yes. Chennai is very completely different. I mean, this is our best weather, so we look forward to this. I'll just close my video. I will switch it on when it is time. What is that? Okay, 5 more minutes. So I'll do.
If I move between screens, do you still see the PDF file that I have, or do you see something else?
Okay, 2 more minutes. Would you prefer the questions to be asked in between or at the end, Mahesh?
I don't mind questions in between. So yes.
So I will keep it then unmuted to everybody, or is
Yes,
it okay?
that should be okay. There aren't many people anyway, so that should be fine. Thank you.
Okay, maybe I introduce you and then it will be 45 by then. Uh, so it is my pleasure to introduce Professor Mahesh Kakde from IISc Bangalore. He has done his PhD in University of Cambridge, and after that he had also he had his position in King's College London. His interests lie in Iwasawa theory, and he and his collaborators have made significant contribution in the theory in the conjecture of Gross and Stark. Today he is going to talk about Brumer-Stark conjecture. We look forward to your talk. Mahesh.
Thank you. So thank you for the kind introduction, and thanks to the other organizers, especially Vijay Kumar, who has put in a lot of effort into organizing this event. It would have been nice to be in person, but this is the next best thing. So thanks a lot. Okay, so I'll talk about the recent work jointly with Samit Dasgupta from Duke on the Brumer-Stark conjecture. So let me start with some historical results. So that's the motivation behind the statement of the conjecture. And then I'll go on after that and say a few words about the proof if I have time at the end. Okay, sorry. So I wasn't sure how quickly my slides would change. So I haven't put any pauses. So the whole information is sort of put in front of you right away, even though that's not how I prefer to do it usually. Anyhow, so let's start. So there's this very classical theorem of Stickelberger from 1890, so about 130 years old, which says, I mean, so the setup is the following. Okay, so you take as a base field, you take the rational numbers, and you take the extension of it obtained by adjoining nth root of unity. Okay, so this is an abelian extension of Q, and there is a canonical isomorphism between the Galois group of K over Q with Z mod nz star. So all units in Z mod nz. Okay, so or I mean, this is just a group. So Z mod nz star is the group with multiplication. And I have deliberately written it this way. So A goes to sigma A. And this sigma A is the unique element in the Galois group that maps zeta n to zeta n to the power A. Okay, so that's the canonical isomorphism between this Galois group and Z mod nz. So that's one side, that's the algebraic side. And we'll consider the ideal class group of this this field K. Okay. On the other side, we have this object which is called the Stickelberger element, and in this case, it's very explicitly defined. Later on, when we move to other number fields, it will not have such an explicit definition. Okay. So this theta, which I'll denote theta rather than theta K over Q, and if there's no confusion, this is defined in the following way. So you take half minus the fractional part of A over N. Okay, so that's a rational number, half minus the fractional part of A over N. And then, so that's the rational number, and sigma A inverse, that's the group element of this group G. And so taking this sum, I get an element of this group ring QG. Okay, so that's my Stickelberger element. That's the element that Stickelberger defined. Okay, so what's this theorem that Stickelberger proved in 1890? So it is clear that n times theta, so now I am assuming n is even, so for this statement, that makes no difference whatsoever, because if n is odd, then q zeta n is same as q zeta 2n. Okay, so you can as well assume n is even, and that makes life easier. So if n is even, then you multiply this theta by n. You get rid of the 2 in the first factor, you get rid of the n in the second factor, and your resulting element, n times the Stickelberger element, it actually lands in the group ring over Z. Okay, so it is in ZG. And the statement is that this element annihilates the ideal class group of K. Okay, so the ideal class group of K naturally has action of G. G is the Galois group of K over Q. And the theorem says that if you hit any element of the ideal class group by n times theta, then you get a principal ideal. Okay, so this is the rewording of that statement. So if you take any ideal in OK, the ring of integers of K, then theta n acting on A, it gives you a principal ideal. Okay, so it gives an upper bound on the ideal class group in terms of this element n theta. That's how one could also look at the theorem, that it gives you an upper bound. Okay. So moving on, how did Stickelberger prove this theorem? So he proved it by factorizing Gauss sums. So Gauss sums are again very classical objects, about 200 years old now. So here's what here's a sketch of Stickelberger's proof of his theorem. So you take any prime number which does not divide n, this, and you fix a prime Gothic p above small p in K. Okay, so p will have some kind of factorization in OK, and you fix any prime above that. And you take the field OK mod P, right? So this is the field with which I denote by F sub Gothic P. That's a finite field with P to the power F elements for some integer F. It's a finite field, so if I take non-zero elements in that, it's a cyclic group, and I fix a generator of that cyclic group. That just helps me define a character chi. From zeta p star, fp star to zeta n, the group generated by zeta n. So this is the multiplicative group generated by zeta n, and it simply sends G to zeta n. Okay, and then the Gauss sum, which I denote by tau or tau chi, is denoted by summation zeta p trace of A chi of A. So this trace is from this field F sub Gothic P to F sub P, okay, Z mod PZ. So the usual, the field with P elements. Okay, so this zeta P to the trace A makes sense, because you can just think of Z mod PZ as 1 to up to P, or 0 to up to P minus 1. So this makes sense. So that's the Gauss sum. And this sum lives in the field K zeta P. Okay, so the extension generated by so this one K zeta P. Okay, that's where this lives. Okay, but you can factorize it, and it's not hard to prove. But I'm not going to go into the proof. So if you take, but I'll just say the following. So if you take any element in the Galois group of K zeta P over K, because P does not divide n, this Galois group will be isomorphic to Fp star, which naturally sits inside F sub Gothic P star. So chi of sigma makes sense. Okay. So if you hit this Gauss sum with sigma, so as I said, Gauss sum lives in K zeta P, then you get chi sigma times tau. So that's how this that's how the Galois group acts on the Gauss sum. So in particular, if I take tau to the n, then every element of this Galois group fixes it, because chi of sigma to the n is trivial. So yeah, because it takes values in this zeta n, right? So So tau to the n, this belongs to k, and I just normalize it in some way. So u is tau n divided by p to the n by 2. So we all know that Gauss sum has absolute value square root of p for any p. For any embedding into complex numbers. So I take this normalization so that this u has norm 1 under any complex embedding. So what Stickelberger showed is that if you hit this particular ideal Gothic P with your n theta, you get a principal fractional ideal which is generated by this particular u. Okay, and the way he does this is he finds the p-adic OR of u under this p and every conjugate of this p. So every prime above small p. Okay, so that's how you prove it. So it's not hard to prove, but I won't say anything else about this. Okay, so so that's how he does it. Okay, he gets explicit factorization of Gauss sum, and that gives you Stickelberger's theorem. Okay, so the existence of these Gauss sums, the existence of this u or sort of Gauss sum is very crucial in the proof of Stickelberger's theorem. The one remark I want to make is that if you take u to the 1 by n, then that lands in an abelian extension of q. Okay, so u to the 1 by n is tau by square root of p, and that lands, maybe I should have a sign here if p is depending on 1 or 3 mod 4, I guess. But anyway, it lands in the abelian extension of the base field. So that's an important remark I want to make for later. Okay, so now I want to talk about generalization of this. So how do I generalize? How does one generalize this? Well, lots of objects were very, very explicit, and it's not at all clear what they mean in a more general context when you're looking at not looking at Q. Okay, but here's the first link that will help one generalize this. So if you apply any character chi of G to this element theta, so chi is a map from G to C star, and you can extend it to a map from QG to complex numbers. So it's a homomorphism from G to C star, non-zero complex numbers, and you can extend it linearly to a map from Q to C. And if I apply if I apply chi to this theta, I get an L value out of it. This S simply means that I may have to take imprimitive L function. Okay, so I may have to remove some Euler factors from the L function. Okay. So this explicit theta doesn't exist for general number fields, but L functions do. So that takes care of one side of the story, and that also tells you that this theta is a very analytic object. Okay, and ideal class group is a very algebraic object, and so Stickelberger's theorem gives a bound on ideal class group in terms of these analytic objects. Okay, all right. So that's one side, and what about the generalizations for number fields? So so instead of Q, you can take totally real number field. Okay, so I can't go into why you take totally real number field and not general number field. There are conjectures for general number field. They are much more technical and more recent than Brumer-Stark conjecture. But so I can't talk about that today. And anyway, we don't have any results on that. Anyway, so you replace Q by any totally real number field, which means that all embeddings of F into complex numbers actually land inside inside of real numbers. So if you like to think concretely, you can just think of q square root of some positive square free number. So q square root of d for some square free positive d. And instead of q zeta n, you can take the narrow ray class field of some conductor n. Okay, so that will replace q zeta n. Q zeta n is the narrow ray class field of q of conductor n. So this is the analog. And now this G has a new meaning. This is Galois group of H over F. Okay. And so there's a theorem of Siegel, Klingen, and Shintani, independently proven by, there are 3 proofs. So Siegel and Klingen use Eisenstein series. Shintani uses some explicit formulae for L functions. It shows that, so you take an element theta in the complex group ring, okay, so CG. So that thing, these L values are complex numbers a priori, right? So a priori there exists an element in CG with this property, okay, with this property. And the content of the theorem is that actually this element has rational coefficients rather than complex coefficients. Okay, so this is some algebraicity result of these L values. Okay, all right. So that's the result of Siegel, Klingen, and Shintani. And this was refined by Deligne-Ribet and Castelnuogas independently. So Deligne-Ribet's proof is a refinement of Siegel's proof, and Castelnuogas's proof is a refinement of Shintani's proof. It says that if W is the number of roots of unity in H, then W times theta is actually in ZG. Okay, so it gives some bound on the possible denominators of theta. And so this is similar to what we had here. Right? N is the number of roots of unity in Q zeta n. Remember, n is even, so number of roots of unity in Q zeta n is either n or 2n, but it's because n is even, it's n, right? So this is the analog of that, an exact analog of that. Okay, so we have these 2 objects. And once you have these, it kind of makes sense, and that's what Brumer did in late 1960s. He said, you take this element W theta in ZG, you look at the ideal class group of H, which is the top field, and this element W theta should annihilate this ideal class group. Okay, so the precise analog of Stickelberger's theorem. That's what he conjectured. So apparently, I didn't know until I wrote this paper that this was never written down by Brumer, but only kind of explained in some lectures and so on. So the statements were made precise, and sort of whatever Stark was doing and whatever Brumer was doing was put together by Tate in his book on Stark conjectures in 1981, I think. So that's why I put Tate's name here. So Brumer's part is that W theta annihilates the ideal class group, and Stark was independently trying to refine Dirichlet's class number formula, and he came up with various conjectures. And so this furthermore part is mainly motivated by Stark's statement. So this furthermore, this part is just a rewording of whatever Brumer's statement is. So if you take an ideal, then you get, and hit it by W theta, you get a principal ideal. So that's exactly what it means, that W theta annihilates the ideal class group. But in addition, if you take the Wth root of this U, this generator, then the resulting extension HU 1 over W, this is abelian over F. Okay. So Stark was trying to refine Dirichlet's class number formula in terms of some, by postulating existence of some units, and it turned out that those units always gave abelian extensions, and so that was also kind of conjectured. So this is what the conjecture, this is what the Stark part is mainly. Okay, so that's the Brumer-Stark conjecture. And this has application to Hilbert's 12th problem, which asks for explicit class field theory. Okay, so you want to explicitly generate abelian extensions of number fields using some analytic data which is intrinsic to that number field. Okay, so you want to generate abelian extensions of F using data that's intrinsic to F. And why does the Brumer-Stark conjecture help? Well, it helps because all these elements U, so as H and P vary, okay, so H remember is also intrinsically defined with from F. It is just the narrow ray class field of conductor N. So instead of H, I could have said N. So as I vary N and P, I almost get the whole, and so the resulting U's, I almost get the whole of the maximal abelian extension of F, which I denote by F ab. I almost get it, well, not quite. I get the maximal abelian CM extension of F, what is called a CM extension of F. And so there's a finite bit left, which is given by some signs. Okay, so you have to adjoin further n minus degree of F over Q minus 1 element. So square roots of certain elements. So but that can be very explicitly worked out. So all these U along with the finite number of explicit elements, that will give you the whole of Q F ab. Okay, so that would be the kind of analog of Kronecker-Weber theorem for totally real fields. Okay, so if you know what these U's are, then this can be in terms of some analytic data, then you can think of this as a solution to Hilbert's 12th problem. Okay, unfortunately, Brumer-Stark conjecture only tells you about existence of these U's, and it doesn't give you any formula for it. Okay, this thing only, this statement only gives you a formula for whatever the odd of this U is. It doesn't, so this is like saying you know norm of a complex number, but that doesn't pin down the complex number for you at all. Okay, so anyway, but Brumer-Stark gives you existence of all these things. So it goes partially towards Hilbert's 12th problem, and now you want a formula. So let me come to the results first. So what are the results? Well, the first theorem, this is on archive. This is joint with Samit. It says that the Brumer-Stark conjecture is true up to 2-part. Okay, so what do I mean by 2-part? So if I take the ideal class group and get rid of its 2-part, so for instance, tensor it with Z1 over 2, then I know that this W times Stickelberger element annihilates it. Okay, so there's some problem at prime 2, as one often expects in number theory. And the problem is not just technical, it's kind of, there's some conceptual hurdle also. So our methods are very p-adic, and so we work one prime at a time at finite primes. But at 2, somehow the Archimedean primes, the infinite primes, should also play some role which we don't quite understand yet. So at 2, there's something to be worked out, some conceptual thing to be worked out. It's not just a technical hurdle that we cannot, that we haven't tried. So there's some conceptual thing as well. So that's for future. Anyway, so Brumer-Stark conjecture is true up to 2-part. But as I said, Brumer-Stark only tells you about existence of these U's. It doesn't give you any way of constructing these U's. So Samit, in his PhD thesis and later, he gave a explicit p-adic analytic formula for these Brumer-Stark units. Sorry for the typo here, and I should have said here that these U's are called Brumer-Stark units. Okay, so he gave an explicit p-adic analytic formula for these. So he conjectured an explicit formula for it. So basically, he constructed a measure on p-adic completions of F, and he integrated some functions, explicit functions, against this measure over F star. And he conjectured that whatever the p-adic number in Fp that you get is the Brumer-Stark unit. Okay, so the theorem star, so this is on archive, that's why I've written theorem. This is theorem star because it's being written, is this conjecture of Dasgupta about the explicit formula also holds up to 2-part. So again, what this means is that he conjectures that U is equal to some other number that he defined, and we can show that the two numbers are equal up to taking some powers of 2. Okay, so so U to the 2 to the something is equal to this to the 2 to the same number. Okay, so up to 2-part the formula holds. And so this is enough for application to Hilbert's 12th problem, because instead of varying P over all primes, you can vary it over almost all primes. You could leave out a finite number. So in particular, you could leave out primes over 2, and you would still get the maximal abelian extension. So, so this can be considered as a p-adic analytic solution to Hilbert's 12th problem for F. Okay. All right. So those are the main results I want to say. And now, what about the proof? The proof. So remember in Stickelberger's theorem, when he showed that this ideal is principal, he already had a candidate here. He had some form of Gauss sum here. So he took the Gauss sum, he factorized it, and showed that and proved that that's equal to this thing. Now the analog of Gauss sums are missing. In fact, so Gauss sums appropriately normalized are the Brumer-Stark units over Q. And we don't know the existence of Brumer-Stark unit without proving this conjecture. So we don't have an independent construction of it. So we can't try to do it the way Stickelberger did. So in fact, what we want to do is we want to prove this conjecture and hence conclude that these Brumer-Stark units exist. Okay, so we don't have this U a priori, which is what makes this very hard. And so the only sort of systematic technique we have for proving, for relating analytic and algebraic objects are modular forms. Okay. But what modular forms do is they sort of give you the wrong direction of than what we want to do in Brumer-Stark. Okay, so Brumer-Stark gives an upper bound on the ideal class group, whereas modular forms give you a lower bound on the ideal class group. Okay, so that's very bad. If you start thinking about this, you want to prove an upper bound, but you only have a method of proving a lower bound. Because modular forms let you construct elements in ideal class group. Okay, more generally, modular forms or automorphic forms let you construct elements in Galois cohomology groups. And so this at first looks very bad, but of course it has been known that if your bounds are sharp, if you expect equality, then you could prove lower bound and then use analytic class number formula. Okay, so this has been sort of well known, and this is how Maser, Wiles, and Wiles prove the main conjecture. They prove so main conjecture is again some form of equality, and they prove one inequality and then use analytic class number formula. So this has been known since Iwasawa. In this case, it sort of is hard because rather than working over a Iwasawa algebra, you have to work over group rings, which makes things much harder. And even proving the lower bound is much harder in this case. So, so a technical comment here is that this is what is called locally P indistinguishable case. So this Ribet's method of constructing Galois cohomology classes is, as we knew, it doesn't work. So we had to sort of, refine Ribet's method quite a bit to get here. Okay, but okay, coming back to Brumer-Stark, so it's an upper bound. Unfortunately, that upper bound is often strict, so you don't expect it to be an equality in general. And so what you do is you try to refine it. You try to get a better bound. And so here is a stronger version. So this is called strong Brumer-Stark, and I believe this is first due to Kurihara, and then maybe independently due to David Burns as well. So instead of saying that theta belongs to the annihilator ideal of something, you say that it belongs to the fitting ideal of something. So fitting ideals are refinements of annihilator ideals. So fitting ideals are contained in annihilator ideals. So fitting ideals are typically smaller, and so there is a chance that this theta actually generates this fitting ideal. Okay, so I should explain some words here. I have to modify my theta. So instead of interpolating this, it interpolates this times this factor. So this replaces W now, and the theorem of Deligne, Ribet, Castelnugas tells you that actually this theta s is already in ZG. Okay, so this factor now replaces W. So that's fine. I need T to have this L to have large enough residue characteristic here, some technical condition, but anyway. And then this is the T modified class group. So somehow this is I won't explain this. This check here means you take Pontryagin dual. Minus means that complex conjugation acts as -1. Because you're taking narrow class groups, so there's complex conjugation in H, and it acts as -1, and it makes sense because I have inverted 2, so taking minus makes sense. Okay, so here's one reason why. So the analog of the stronger statement for, sorry, I'll just take 2 more minutes. I'm almost out of time. So the analog of this this strong version, when 2 is not inverted, is also not clear what exactly it should be. So that's one of the difficulties. Anyway, so you have a stronger version that theta st belongs to the fitting ideal. Now, unfortunately, even that is not good enough, because even this could be strict inequality. So the ideal generated by theta could be strictly smaller than this fitting ideal. And now you sort of seem to be stuck again, but fortunately you go and read various papers of Burns and Kurihara, and they have modified this theta. So this is a very technical statement. These objects don't look very familiar if if you don't work in this area of equivariant Tamagawa number conjecture and so on. So they replace the ideal class group by some modification, Selmer group. This is called a Selmer group, and then this theta is replaced by something else as well, and then they conjecture that there is an equality like this. So actually, this is not quite true, because Burns makes a different conjecture in terms of so Burns actually defines an algebraic object whose fitting ideal is expected to be this thing, and Kurihara defines an ideal which is not a principal, which is supposed to be the fitting ideal of this class group. And so we sort of just came up with a statement which was a mix of two, so somewhere in the middle, and that was good enough for us. But anyway, this is all inspired by Burns and Kurihara, so we can't take any credit for this statement. So this conjecture of Burns and Kurihara, it implies the strong Brumer-Stark, and that in turn implies Brumer-Stark. And just a last word. So now that we have an equality, what we do is we use modular forms to first show the inequality in this direction. So the fitting ideal of this is contained in the ideal generated by theta tilde. And then we use the class number formula to bootstrap this inequality into an equality. Okay, so we use Hilbert modular forms to show that this thing. So this is some refinement of Ribet's method, and then we bootstrap it using class number formula to get the equality. Okay, so thank you.
Thank you, Mahesh, for the nice talk. Is there any question from the audience? You can unmute and ask the questions.
I had a question. The Stickelberger element, use of Stickelberger element is just to principalize some ideals, right?
Yes.
Okay.
I mean, it is, but the way to think about this is that you get an upper bound in terms of some L values. Okay, so you get an upper bound on the order of ideal class group or various components of ideal class groups in terms of some L values. So that's the non. I mean, you look at class number formula. So it tells you, it gives you order of the ideal class group in terms of leading terms of the zeta function, at s equal to 0, if you want to, that's if you want to put it in this language. So in terms of leading terms of the Dedekind zeta function at s equal to 0. So that's why it's non-trivial, because it tells you something about the, I mean, you know that the ideal class group is finite, but now you have a formula for it in terms of some analytic object. So this is similar.
Okay, thanks.
Is there any more questions? So I will ask you something. Just can you explain a little more about this problem at 2 part? What is the conceptual problem?
Yeah, so the first problem we face is that, well, for instance, if you haven't inverted 2, then minus part doesn't make sense.
I agree. To this, other than this, is there?
So no, I think this, I mean, somehow the whole thing is kind of interlinked. So once I think you make a proper, you make a good general statement without inverting 2, this kind of statement, then I think our method should more or less be sufficient to do it. I think apart, I mean, again, sort of the other problem is somehow in the you go from Hilbert modular forms to Galois representations, and there you have to diagonalize something. So you have to pick a nice basis, and then after that you have to diagonalize something. So there again we invert 2. So there are lots of local conditions that we have to satisfy for these Galois representations. Now, because we don't have a good statement here, I can't say this for sure, but I think if we have a good statement here, then the problem there will also be sort of guided by what statement we have here. So there are problems in two places. One is to get the right statement of this strong form, and the other is somehow in the construction of Galois cohomology classes. But my feeling is that they are related. So if we solve one, then the other will somehow follow.
Thank you, Mahesh. Is there any more questions? If there are none, let's thank the speaker for the beautiful talk. Thank you.
Thank you, Mahesh Kakde and Sonali Gunn, for spending their valuable time with us. Next, we have again an invited talk by Sonali Gunn at 11:45 p.m. Indian Standard Time. Thank you very much.
Thank you.